This is chapter 5.3, Associations and Categorical Variables. In this section, we're going to continue our analysis of two-way tables and use probability to determine whether two categorical variables are associated. So let's start with an example. The following two-way table classifies each person that was on the Titanic by class and by whether or not they survived the ship's sinking. So first thing, notice that we've got class up here in our column headings, first, second, and third class, and also crew. And we also have whether or not they survived the ship sinking over here. There's our second variable. And we can also make note down here that there were 2,201 people on the Titanic when it sank. All right, so let's use this table to calculate the following probabilities. So first probability, what's the probability that a randomly selected passenger was in first class and survived the disaster? So note we're looking for an and statement here. All right, so we're looking for all of the passengers. There were 2,201 of those. That's our denominator. And we want all of them that were in first class and survived the disaster. So first class is in this column. Survived is in this row. So we want that overlap. We want the 203 passengers that were in both of those categories. So that's roughly 9%, or about 9.2%. Second one, what's the probability that a randomly selected passenger was in first class or survived the disaster? It's a little bit different. We've got an or statement. All right, so first class or survived. So if you go back up, we had 325 passengers that were in first class. We've got 711 passengers that survived. Oops, and that should be a minus sign coming up next. So we need to take out the overlap, and that's the 203 passengers that were in both. And that's out of 2,201 passengers. That's 833 passengers out of 2,201, or about 37.8%. And the third one, what's the probability that a first-class passenger survived the disaster? This one's a little bit different. This one we're looking at the first-class passengers to start. So not all 2,201 people. If we go back up, we just want to focus on the 325 people that were in first class. So out of those 325 people, how many of them survived? So go back up. There were 203 people in first class that survived the shipping, or the sinking rather. So 203 out of 325 is about 62.5%. And so our last question here says, to note the first two probabilities require the and or rules for probability. How does the third question differ from the first two? Well, the third question, again, had us focus just on one set of these, or subset of these passengers, just the first class passengers, whereas the first two had us look at all of the passengers. All right, so the third one, again, this one here, it's a little unusual, a little bit different. We're taking it as a given that the person is in first class. Those are just focusing on the first class passengers and what proportion of them survived. This is what's known as a conditional probability, and we're going to take a closer look at these in the next few pages. Okay, so on the next page, number 3, let's use the following Venn diagrams to represent the data needed to answer each of these previous questions. So we've got the table reprinted here just for convenience. So in this table, we've got the following table, we've got the 3 questions again. And so first one, what's the probability that a randomly selected passenger was in first class and survived the disaster? So that's that and statement. Remember, the and is looking for the intersection between these two. So we want to know how many people fit into both of these categories. So keep in mind that there were 203 passengers that fit into this intersection of the two groups. In fact, if we look, there are 325 passengers in first class. And let's see, survived was 711. And again, the intersection was 203. So we got 203 out of 2,201. Second one, the or statement. What's the probability that a randomly selected passenger was in first class or survived the disaster? Where that's interested in looking at both circles together. So if we've got 325 passengers in first class, 711 passengers that survived, and we know that there were 203 that had both, that were first class and survived. We look at the rest of this circle on the left, the yellow one. We've got 122 passengers in first class that did not survive. And then this blue portion of this circle, subtract that, we get that there were 508 passengers that survived that were not in first class. So the OR wants all three of these groups. We had 122 from the first part, 203 plus 508. And notice we're doing this a little differently than we did in the previous problem. And that gives us the same answer as before, 833 passengers out of 2,201. So just as an aside note, on the previous page, we did this by taking 325 plus 711 and then subtracting the overlap because that got counted in both circles. And again, that gave us the same answer as what we just did. And I was missing a 1 there. All right, so in the third one, the one that was a little bit different, what was the probability, or what is the probability that a first-class passenger survived the disaster? Notice that all we really need from the above diagrams is a circle on the left, the one for first class. So we're going to label each part of this Venn diagram. So this is the 325 people that were in first class. This left-hand side of the circle, the yellow portion, represents, let's see, we take 325 minus the 203. This is 122 passengers, remember, that were in first class but did not survive. So this is first class passengers that didn't survive. Okay, on the right-hand side, we've got the 203 that were in the overlap from above. So that's this portion here. And this were the first class passengers that did survive. All right, so taking just the first class passengers as our group, we've got 325 people. And we want to know what proportion or what was the probability that they survived. So we just want the 203 out of the 325. And this was roughly 62.5%. Okay, so number 4, that last probability that we just did, so from above, asked us to focus on one specific group of people. That was the first class passengers. And then find the number of people within that group that survived. Probabilities such as these are referred to as conditional probabilities. In this case, we're finding the probability of surviving conditioned on having been in first class. In other words, we're assuming that we're focusing on just the first class passengers. So there are 3 common ways to phrase a conditional probability. First one is to find the probability that a first class passenger survived the disaster. Second bullet here says that you need to find the probability that a passenger survived given that they were in first class. And the last one is what proportion of the first class passengers survived the disaster. So notice that each of them in their own way is telling you to focus on just the first class passengers. Right, so number 6, let's take a look at the mathematical notation for these conditional probabilities. Right, so for our Titanic example, we've got P for probability. Notice within the parentheses, we've got 2 pieces. If the passenger survives and the passenger was in first class. And then we've got this vertical line here. And that corresponds to this piece here given. So if we read this statement, it's read as the probability that a passenger survives given that the passenger is in first class. So you're focusing on this group here. This is the subset of the passengers that we're interested in. And then the first part is, what about those people? What about the first class passengers are we interested in? So in general, a conditional probability looks like this. So again, we've got P for probability. Notice we've got that vertical line again for given. And so if we read this, it says the probability that event A happens given that event B happens. Right, so next question, how do we find these? How do we find conditional probabilities? If we have access to a two-way table, then we can isolate the group from which we are sampling, the first-class passengers, and then find how many of that group survived. If we don't have the two-way table, then we can use the following formula. And just another reminder, we don't need to memorize, you don't need to memorize these formulas. We'll give them to you for the test. So if we look at this, this is looking at the probability of event A given that B has happened. And over on the right, we've got two familiar probability statements we've seen before. Top part is the probability of A and B, so it's an and statement. And the bottom part is just the probability of B. You can also think of this as a probability of A happening within B. All right. Okay, so let's use this formula to calculate the probability that a passenger survived given that they were in first class. So again, assuming we didn't have that table, how could we do this? We already know that the answer was 203 out of 325, or again, roughly 62.5%. So I'm just taking that from our previous work. But if we use this for our formula, let's see, first thing we want to do is specify it or make it specific to our question. We're interested in the probability that the passenger survives, given that they were in first class. Okay, so this is going to be the probability of survives and first class. I'm going to abbreviate that to first because I'm running out of room, over the probability of being in first class. Let's try this out. So the top part of that, probability of survives and being in first class, is 203 out of 2,201. Second probability, the one from the bottom, it's the probability that somebody is in first class. There were 325 passengers out of 2,201. So you can plug that into your calculator and verify that that's 62.5%. But let's just take a quick refresher here on how to divide two fractions. So I'm going to write that first fraction in a more vertical format and switch the division sign in the middle to the one you typically see on a calculator keypad. So that's what our division statement looks like. And this is where the refresher comes in. Remember, when you're dividing fractions, take that second fraction and flip it over, and it becomes a multiplication statement. And from here, we can see that the 2,201 cancel each other out, and we get the probability that we found from the table earlier. All right, so number 9, we're going to use this formula again. We're going to find the probability that a passenger was in first class given that they survived the disaster. So notice it's a little bit different. The order of the statement is a little bit different. So if we use this formula and we write it out specific to this problem, with the probability that someone is in first class, given that we know they survived. So we're conditioning on a different group. So using this formula, the top part of our expression is going to be given that the probability that they were in first class and survived. And this time our denominator, oops, a little bit too far there, is the probability that they survived. Okay, so putting in some numbers here. You know the top part of this is 203 out of 2,201. And the bottom part, the probability that they survived, you might need to go back to your table to verify this, but there were 711 people that survived out of 2,201. So if we calculate this, we know these 2,201s are going to cancel. We're going to be left with 203 out of 711, or roughly 28.6%. So notice that's quite a bit different from what we did above. And quite a big difference in these probabilities. At 28.6% here, and 62.5% up there. Now in number 10, are these probabilities in number 8 and number 9 the same? They're not. So number 11, does the probability in number 8 equal 1 divided by the probability in number 9? So remember, the probability in number 8 was 62.5%. So does that equal 1 divided by the probability number 9? You get that these are not equal. So put a slash to that equal sign. These are not the same. They are not equal. So what does this mean? Well, number 12, our answers to number 10 and 11 should both be no. These two questions illustrate two important features about conditional probabilities. First thing is that the order of the condition is important. We just found, for instance, that the probability of A given B is not the same as the probability of B given A. So if we take a closer look, number 8 was limiting our attention to the people in first class. Number 9 was limiting our attention to the people that survived. So switching the order of the conditioning meant that we were looking at a different subset of those passengers. And then the second thing, the given line, this is really important. Remember that given line, that vertical slash here, that's not a division sign. So it doesn't say anything about dividing that probability of B by A. There's a formula for it that we saw above. Again, it doesn't mean division though. Okay, so let's return to our original question. How can we determine whether two categorical variables are associated? So let's continue with the Titanic example. Are passengers, class, and survival associated? So the table again is copied below. So we're going to find some conditional probabilities to get us started. So first one, what is the probability that a first class passenger survived? So we're looking at the first class passengers. We want the proportion of them that survived. So that's 203 out of 325, or again, roughly 62.5%. All right, second probability. What's the probability that a second class passenger survived? So now we're limiting our attention to just the second class passengers. And in that group, there were 118 that survived out of 285, or again, roughly 41.4%. Third class passengers, what's the probability that they survived? I'm going to go back up to the table, going over to the third class column. Notice that there were 178 passengers in that group that survived out of 706. Or roughly 25.2%. Right, and the last one here, what's the probability that a member of the crew survived? So now we're limiting or restricting our attention to the crew members. And there were 885 crew members, 212 survived. So our probability is 212 out of 885, or roughly 24%. Right, so is the probability that a passenger survived the same for each class? Just found that they're not. If you go back up, looks like it's more likely that someone in first class would have survived, less likely that a member of the crew survived. So first class passengers were more likely to survive. And so again, first class passengers were more likely to survive. Okay, number 14, since these probabilities are not the same, the passengers class was associated with the probability of their survival. In other words, class and survival are associated. So that's the key here. We're seeing that these two variables are associated. This can be illustrated with the following segmented bar graph, which was created in StatCrunch. So notice it looks a lot like a bar graph, but there are segments within each bar. So again, we refer to these as segmented bar graphs. Got a key over here, or legend on the side. Tells us that the lighter gray portion, or lighter gray segment, is for those that survived or alive. The darker gray, the black segments of the bars, are for those that died. So how does the segmented bar graph show an association between class and survival? Well, notice that class is down here on our horizontal axis, and we've got a bar for crew, first, second, and third. And then we've got survival over here in our legend. Okay. So how does it show us that there's an association? Well, notice that the segment for alive has a different height within each of these classes. And then the first class here has the largest segment for this survived group. So they had a much higher probability of surviving. Crew had a much lower probability of surviving. They had the smallest segment for the alive or survived group. Right, so since these segments indicating how many or what proportion survived are all different, that's what's showing us that there's an association between these two variables. So number 16, what would the segmented bar graph look like if there was no association between class and survival? So I'm going to change my legend here. I'm going to use green for alive or survived, and I'll use blue for died or didn't survive. So if that were the case, there was no association between these two variables, then we would see that each segment for the alive group, let me switch colors here, was the same across all 4 classes. And as a consequence, that means the segment representing those that died, or the proportion that died, is also the same for each of these 4 classes. In other words, it doesn't matter which class you're in, the probability that you survived the accident or the disaster would have been the same. And one last comment about those, just keep in mind if you're dealing with sample data and you're looking at a segmented bar graph, that these heights, you're looking for whether or not 2 variables are associated, they may not be exactly the same, and that's due to the idea that you're taking a sample. There might be some variability in there. So we're looking at whether or not they're very similar. Okay, if 2 variables are not associated, then they're said to be independent. So if the probability of survival had been the same for all classes, then we would say that the class and survival are independent. Knowing which class a passenger was in would not help us predict whether that passenger survived the disaster. So we go back to our segmented bar graph. Let's look at that second one. Since there's no association in this one, that means that class and survival, remember this is the made-up graph, are independent in this example. So if they're not associated, then we're saying that they're independent. So back to number 17. 2 events are independent if knowledge that one event has happened tells us nothing about whether or not the other event has happened. So the mathematical notation for 2 independent events is, we've got probability of A given that B has happened, should be the same as probability of A happening. And it doesn't matter if B happened or not. And then the reverse, probability that B happens given that A happens, should be the same that probability B happens, or probability of B happening. Again, it shouldn't matter whether or not A happens. So let's take a closer look at this formula. And again, no need to memorize this. So we've got the 2-way table reprinted here for our convenience. So we're going to use these formulas and see what happens. All right, so probability that the passenger survives given that they were in first class. So given that they were in first class, there were 325 passengers there. And those that survived, there were 203. And that again is about 62.5%. Probability that a passenger survived, there were 711 passengers that survived. Notice that's not a conditional statement, so we're looking at all 2,201 passengers. And that's about 32.3%. Let's note that these are not the same. Okay, so if we think of this as the probability of event A happening, given that B has happened, so we've got passenger survived as A, first class is B, then this one is the probability of A happening. So we're showing that this first statement is not true. So we got 2 different probabilities, and this is then showing us that class and survival are associated. In other words, they're not independent variables. So the question, how close do these 2 probabilities need to be to conclude or determine independence? When our 2-way tables are based on sample data, the values may not be exactly the same, even if the events are independent. So there are other tests for independence. They are in chapter 10, which we won't get to this semester, but other statistics classes, if you go on, you'll revisit this idea. Okay, so number 19. Following sample space contains the 8 possible outcomes for the random process of flipping a coin 3 times. So use this sample space to calculate the following probabilities. So just a quick note here. This first outcome represents flipping a coin 3 times and getting tails each of the 3 times. And one other example, we'll take another one here. this outcome shows us that the first coin toss was tails, followed by 2 heads. So first question, what's the probability that I get a tail followed by 2 heads? Well, there's only one outcome where that happens out of 8. So that's 1 out of 8. Second question, what is the probability that I get all heads? There's only one outcome out of 8. Again, that satisfies that. So the probability is 1/8. The last one here, what's the probability that I get at least one tail? Well, now I have to go back up and look. At least one tail. So I'm going to make a check mark. See, those both have tails. At least one tail. This one doesn't. So I'm going to put an X there. But these other 3 all have at least one tail. So at least one tail is really the same thing as 1 or more. So this probability is 7 out of 8. Notice that these 2 events are complements of each other. And if you get all heads, the only other thing that can happen is you get at least one tail. So if I take 1 minus 1/8, probability of getting all heads, notice that I get the second probability or last probability here, probability of at least one tail, which is 7/8. Right, so note that the result of the second toss is independent of the result of the first toss, and the result of the third toss is independent of the results of the first and second tosses. So it may seem intuitive that the result of each toss is independent of each previous toss. If the results of each toss are independent, then the probability of heads on each toss is always 50%, regardless of what happened on each previous toss. And since these events in each sequence above are independent of each other, we can use the multiplication rule to find the above probabilities. So here's our multiplication rule. We want the probability of event A and B happening, and A and B are independent, then we can do the probability of event A times the probability of event B. Note that this rule can be extended to more than 2 events. Probability of A and B and C, if they're all independent, is just the probability of A times the probability of B times the probability of C. And so if I go back up, let's try this out on 1 or more of these. Let's try at least the first one. Since all these coin tosses are independent of each other, this first statement can be written as probability of tails on the first toss and heads on the second toss and heads on the third toss. And that means we should be able to take the probability of getting tails times the probability of getting heads times the probability of getting heads. And probability of tails, assuming the coin is fair, is 1/2 times 1/2 times 1/2, which is 1/8. So we get the same answer from the sample space that we can get from this formula. And then just a last note about this probability rule. If you're interested, you should read the case study on pages 205 to 206, and there's a follow-up on page 232. Very interesting application of these probability rules.